All right, so we have Kenichi Ohshika, and he'll be telling us about the Thurston metric.
Thank you very much, and thank you very much for coming back. And so the last two talks, I talked about the Thurston metric on the Teichmüller space. So today I'm going to talk about another metric, another fissural metric, which is called the earthquake metric. So that's in the title, so the earthquake metric on the Teichmüller space. So what I'm going to talk about today is all the collaboration with Yuping Pan and that probably the order is wrong. So the Yifang, and the Athanase, and the Yuping Pan. Okay. So we start from something very elementary. So let me just remind you of the Fenton-Nielsen twist, which was extensively explained in John's talk. So we have some closed simple. Suppose we have some simple closed curves on a surface, simple closed geodesic on the surface. Then we cut the surface along the closed geodesic and glue it back after twisting the one side of the surface by some length. So that was called the Fenton-Nielsen twist. So we just twist it and glue it back. So that's the Fenton-Nielsen twist. So probably for this C, there's another data which is the twisting distance D. So this should be called the Fenton-Nielsen twist along T times C. Or along C of distance D or something like that. And what I'd like to show today is a kind of a generalization of this kind of the Fenton-Nielsen twist first. So it's called earthquake. So it's something invented by Thurston. And this is a generalization of the Fenton-Nielsen twist too. So here the twisting was done along a simple closed geodesic. But for the earthquake, it's along something more general. It's a major lamination. So this is something analog to the Fenton-Nielsen twist, but the locus of the twisting is a major lamination. So we introduced this symbol the last talk, and it's a major lamination space on the surface S. And it's so in the last talk I told you that the set of the simple closed curves, that the set of the isotopic classes of the simple closed curves multiplied by this scalar is dense in this space. So this Fenton-Nielsen twist. So suppose you have a major lamination here, then there is a sequence of the weighted simple closed curves converging to lambda because of density here. So let me write it in this way. So French-Tunisian, what's a good symbol? Probably the French C, D, like that. And then this deformation, French-Tunisian deformation, defines the map from the Teichmüller space to Teichmüller space, because for every hyperbolic structure, we can draw the same homotopy. So we can draw a closed geodesic corresponding to some same fixed isotopic class of the reciprocal curve. And so starting from every hyperbolic structure, we can do the same operation. So that operation gives a new hyperbolic structure, so that we have a map from the Teichmüller space to Teichmüller space by taking the hyperbolic structure to the one obtained by the French-Tunisian twist along C of the time t. And it's rather obvious that it's a bijection, and also rather intuitively it's clear that it's continuous, and then the inverse is also continuous. So this is a homomorphism between the Teichmüller space and the Teichmüller. So it's an auto-homomorphism of the Teichmüller space. And so we written here, so that you have a lambda, a measured lamination. So we have a sequence of simple closed curves converging to that. And then we see that this Ti converges to some homomorphism from the Teichmüller space to Teichmüller space uniformly on every compact set in the Teichmüller space. So that's what's called the earthquake. So this is just kind of the formal definition, but so there's some intuitive interpretation of what's happening here. So you have a geodesic, you have a measured lamination, which is realized as a geodesic lamination on each hyperbolic surface. And then instead of just cutting the surface along a simple geodesic and twist, so you can just consider something like a sliding, land sliding along this measured lamination, and what to get is this map. Okay. So the yep.
So what exactly is the measuring? So in the case of a simple closed curve,
yep.
does the parameter
Okay.
Right. Shift to a tail twist?
Yeah. Yeah. Okay. Right. Yeah. So okay. So let me explain what's happening. So that if you consider something like that, so you have a measure, and so this is mapped to something like this, and the total amount of this sliding is the measure here. So this kind of land sliding is performed so corresponding to the transverse measure. Sorry?
It's measured in terms of the hyperbolic.
Oh, measure is a transverse measure, something fixed.
Yes.
It doesn't have anything to do with the hyperbolic structure. So the measure is a transverse measure fixed on that. So this doesn't depend on the hyperbolic structure. And so an infinitesimal version of this one is something called the earthquake vector. So you consider the Et times lambda. So lambda is a measured lamination, and we consider the E times something. So X is a point in the Teichmüller space. Then we can consider this. So as T varies, so that you get some kind of an arc in a Teichmüller space. So at the time T is 0, so it just means it's identity. So starting 0, so that in a Teichmüller space, you have X, and then you have an arc like this. Okay. And you consider the derivative of this, and at the t equals to 0, you get some tangent vector. And that's denoted by something like this. Okay. So it's a tangent vector. Okay. Any questions up to here? Okay. Right. Now the fundamental theorems in this field, I mean in the field of the earthquake maps, is the theorem by Thurston, and also its infinitesimal version proved by Kirchhoff. So for the Thurston theorem, so for any 2 points, X and Y in the Teichmüller space, there exists a unique measured lamination such that Y is the image of the earthquake along lambda from X. Okay, yeah. And the second one is this is proved by Kirchhoff actually. So this is infinitesimal version of the first one. So for any vector, tangent vector, of the Teichmüller space, there exists a unique measured lamination such that V is equal to the earthquake vector along lambda at X. Okay. Sorry? Okay, so so it's actually the proof is actually Thurston himself gives some kind of proof, but the formal proof is contained in the Kirchhoff's paper on the analysis of the earthquake. So because these earthquake maps are actually analytic, so locally it gives a kind of something like exponential map is well defined. And that gives such a kind of theorem. So now we can define earthquake metric or earthquake norm. So for tangent vector V, so we define the earthquake norm to be the length. So because of that, so V is expressed as a earthquake vector. Then this and this one is unique. And so the earthquake norm of V is defined to be the length of this measured lamination. Okay. So it's easy to check this. This is this is, by the way, this is something like a symmetric norm. So we don't have as before, we don't have minus V, the norm of the minus V equal to V, but the norm of V, we don't have that. But even the triangular inequality is not so clear if we just consider this definition. So this one is not so easy to see. It's not trivial at all. So let me show you how to prove that. So to prove that, if you have a norm, then if you like to show the this kind of the triangular inequality, then it's equivalent to show the convexity of the unit sphere. So we consider V such that the norm is equal to 1, and then we denote this by sigma sub x. So we already used in the last two talks, we already used the S of x to denote the unit sphere with respect to the Thurston norm. So this time I will use sigma as a symbol. Okay, and so if we can prove that this is convex, then this follows. Okay, these are the two are the same thing. And for that, so this is a bit tricky. So you consider something like V on a unit sphere, and so thanks to this theorem, so V is always expressed as the algebraic vector. So I will drop the x from now on, because I'm always staying inside the tangent space at x. So that we drop this x from all the symbols. X from here. Okay, I mean, probably I preserve this subscript x. Okay, and then you have V. So now let me remind you of the unit sphere with respect to Thurston norm. So this is different from that. So this is unit sphere with respect to the Thurston norm, which I talked about in last week. So here, so you have some vector V, okay? And the dual of that was projected lamination, so the measured lamination space. And so that every hypersurface of this unit sphere can be expressed as a d log, for what's a good symbol? D log something like, probably it's not, yeah. Wait a minute, what's a good symbol? Yeah. Okay, probably it's better to like d log L mu. Okay. I don't need this okay, yeah, just reverse that. So that V, so you have V, so that some hypersurface d log equals something constant gives a hypersurface for V. Probably because the norm of V with respect to Thurston norm is not known. So but anyway, so that gives a hypersurface touching at this Sx at V. Okay. Right. Okay. Okay, and so So that means you have, so in this case, you have V here. And you, so as I explained last day, so you have V here, and then you have some phase. And you have something like d log mu. Okay. And so we can take, probably it's, okay. And if you change mu, so you get different hypersurface. But this so at V, so you consider all the set of the hypersurface. So probably you change this to lambda, and consider the value at V. If you vary lambda, so for any other hypersurface, which is not tangent at V at this point, then so you imagine a picture like this. You have a hypersurface here. This is this should be something like d log mu. But if you consider any other hypersurface like that, then this V, this point V, is below this hypersurface. So that means this value attains maxima at lambda is equal to mu. Okay. Okay. Because if you change the hypersurface, then except for those touching at V, tangent at V, so the value of the V is smaller than equal to this, if it in a unit sphere, this should be 1. So probably it's better to consider the case when the V is, so by multiplying the scalar, if necessary, we can consider the case when this is really unit sphere. So if you consider the other hypersurface, which is d log something equals to 1, then this V is on the other side of this one, the same side as the B, this unit ball is. So the value should be less than 1. So only for those hypersurfaces touching at B attained this value 1. So this is attained maximal when lambda is mu. Okay. And V is also expressed as a algebraic vector by this theorem. So we have the situation like d log lambda E mu attains maxima at lambda equals mu. Okay. On the other hand, so there is a Kirchhoff sine cosine formula saying that this is equal. So if you consider the two major lamination and consider this is equal to the E lambda d log L, sorry, this is L lambda, sorry. Then this is just the evaluation of this length function with respect to this tangent vector. And the Kirchhoff's formula says that if you exchange the mu and lambda, then you get just a minus. So that this is something like E lambda L, something like that. So this means that if you, so at this point lambda, so you get you have a hypersurface which gives a minimal value of this vector. Okay. So that means this shows the convexity of the point at the point d lambda with respect to this the R-square norm, because this was given as a minimal point of this function. So such an argument, well, this is a bit complicated, but such an argument shows the point is that you have this triangle inequality. Okay. And now, so this is just a norm. So the distance is just a Fisher metric with respect to this norm. So it's just the infimum of the norm. So where alpha joins x to y dt. Okay? This is just a definition of Fisher metric as appeared in Bank Stuart's the talk. Yep. So again, this is asymmetric. So there's no symmetry for this metric, but you can define a metric. Okay. Now, so we have such a kind of for instance, we have Fenchel-Nielsen twist, and we have a continuous family of the Fenchel-Nielsen twist, which is a ray starting from this base point x. In the same way, as written here, we can consider a earthquake ray starting from some base point x. So then if we define the metric using the earthquake, then it's natural to imagine that this earthquake path might be geodesic with respect to this distance. But actually, this is not the case. So let me explain why. So we don't know if the short earthquake path is geodesic or not. But what we can show is that at least if it's long enough, it cannot be geodesic. So let me show you. So the long earthquake path are not geodesic with respect to this earthquake distance function. So let me show you by an example. In general, this is a bit difficult to explain, but the Fenchel-Nielsen twist case is very easy to explain. So you start from, for instance, you have a surface S and a simple called geodesic C, and you consider a Fenchel-Nielsen twist. So if you just use the same symbol as the earthquake, that should be TC. So starting from X, TC of X, and you have a family of the twist, and it gives a ray starting from X. So it's so you can go further and further by making T larger and larger. And so let me show you that this cannot be a geodesic if the T is very large. Why? So you first consider pinching of this simple closed curve along C. So make it very short, something like this. Okay. And so, and they consider twist along this short one at the same amount. So you consider this, or probably the case when t is integer is easy to understand. So that this should be something like integer. Okay. And so because this is the image of this one by some action of the Dehn twist, which is inside the mapping class. So if you can pinch it by distance k, then you can pinch this by distance k to this is something like so what should be x prime, and this is you can pinch this one in the same way, like as here, so that the distance here and the distance there must be equal, because it's the image under the mapping class. So they are isometric. So this should be the same amount of the distance. And now, so if the length of the C is something like L, then the distance from here to there, so if you consider something like this along this curve, then if you just, so if you consider the unit Fenton-Nielsen twist, because the length of C is L, so this is the length of C at X. And so if you just do it m times, then ml square should be the length of this one. Okay. Now, on the other hand, if this length C, this must be very small, maybe put it like L. So L is very small compared to L. Then the distance here, not the distance, the length here is something like m times small l squared. So if you consider the concatenation of the three parts, here, there, then it's 2k plus m small l squared. And because L is very small compared to L, so if this capital L is large enough, then this should be very large compared to that. So this part, this concatenation of the parts is much shorter than this one. So that there's no way that this one is geodesic. Yep.
How did you estimate ml squared as the
Okay. So if you just consider the unit twist, meaning that just distance one twist and it's a derivative, then it has the earthquake norm of this one is equal to L by definition. So the earthquake norm is equal to the length of the lambda, and the lambda is C in our case. So this is the norm, okay? And to get the full twist, I mean a Dehn twist, you have to travel L if you measure it by a unit length. So to get the full twist, you need L square. And we are considering the m times full twist, so that should be m times L square. Okay. Pitching is something constant. So it might be very large, but it's you have some constant anyway, depending on C and the X and everything. But you have some constant. But it's independent of M here. So if you just then twist M times then twist, then this K and this K are equal. That's the point. So this might be very large, but if you make this capital L larger than this, then you get this. Yep.
So is it right that the K's are the same because
yeah, it's because it's then twist. Yeah, right. So it's just the image and the mapping class. So well, even if it's not a then twist, we can argue in a similar way because if you consider the interval from this to the first time then twist, then there is a compactness of so this distance is bounded by some constants, so that you can argue in the same way. But the case when it's full then twist is very clear. Okay, any questions? More? No? Yeah. It's not globally. They're not length minimizing. So our definition of geodesic is something like global, not the geodesic in the sense of differential geometry. So if the length is equal to the distance, that's called the geodesic. So that's our definition. Yep.
So this is it says that so you're saying that for large L this is not true.
Right.
So that means for certain points in the Teichmüller space, it is not a geodesic.
Right. Yeah. I mean, for the shorter one, we don't know. Our conjecture is that for any short one, and that cannot be geodesic, but we haven't proven it yet. So that what we proved is just if it's long enough, then it cannot be geodesic.
No, you said so you proved that if the curve is long enough, it is not.
Curve is, I mean, M is large enough.
If L is large enough.
M is large enough. The length of this one it doesn't matter. You can pinch it anyway. Okay, next I will talk about the duality of the this earthquake norm or earthquake metric. So here the theorem which is known to Thurston. Yep.
This is trying to relate it to something in the Teichmüller metric.
Yep.
So the earthquake flows are supposed to be something like horosic.
Yes.
Right? And whereas here you are expecting that for small distances you are getting close to geodesic. So I mean, how do these two pictures sync?
The earthquake flow is holocyclic, but at the same time, this norm looks like a bit holocyclic kind of metric. So that there might be an expectation that these two coincide, that this might be a geodesic, but it's not the case. That's what I'm saying. So here's the theorem. So for any x in the Teichmüller space, so there is a linear isometry from tangent space with respect to this earthquake norm to a cotangent space with respect to the Thurston norm. Okay. So let me show you how to prove this. This is, the proof is short, but it contains somehow the notion which is not so simple. So let me remind you of there was something called the Veil-Peterson form, which appeared in Sumio's talk. So, and there is, so there's a Veil-Peterson form. And that was defined on a complex vector spaces, right? So the Peterson form was defined on the space of the holomorphic quadratic differentials and its complex space. And so this dual of that is a Veil-Peterson form, which is defined on the space of the harmonic Beltrami differentials. Okay. And so you have a form, something like that. And probably, so if I'm not wrong with the coefficient, so so this is the imaginary, the number times v, then probably 2 times real. This should be the something called the Veil-Peterson symplectic form. Symplectic form. Okay. So it's so Riemannian. So Veil-Peterson Riemannian metric was obtained as a real part of this HWP. So it's something imaginary part of the same form. So that's called the Veil-Peterson symplectic form. And we can define the linear map from the tangent space to the cotangent space by this. So just consider the V is equal to the omega WP, and we fix V here. Okay, this is a linear map, and so that it contained in this is a linear map from the tangent space to the linear function from the tangent space, so that it's contained in the cotangent space. Okay. Right? Okay. And what's essential here is the following formula proved by the Wolpert. So he showed that the earthquake is sent to the derivative of the length by this map. So phi of sub WP of the earthquake is equal to the derivative of C at any point of the Teichmüller space. Okay? So taking a limit, for general, so this was a simple code geodesic, but in general, taking a limit, you get the same equality. So for any major lamination, you have this. But this turned out to be by the definition of, or just the derivative of the log L lambda is equal to the derivative L lambda divided by the length. So this is equal to that. Okay. Right. So this says that, so here we recall that the norm of this one was equal to the length. Okay. And here, the conorm of this one, so this was embedding of the projective lamination space to the unit sphere in the cotangent space, as I explained in the last talk. So the conorm of this one is equal to 1. So the conorm of this one is, of course, equal to the length. Okay. So this map preserves the norm. I mean, from the earthquake, so this is isometry from the earthquake norm to the Thurston conorm. So this gives actually, so this map actually gives an isometry from here to there. So that's the proof of this. Any questions? Okay. So this is something called a duality. So in some sense, to understand the tangent space of the earthquake norm, you can just look at the cotangent space of the Thurston norm. So this is somehow amazing. And actually, what's important here is you use the Wien-Peterson pairing. So Wien-Peterson pairing is somehow the combination of the complex side of the Teichmüller space and the hyperbolic one. And so that plays some role to give us this duality that, that's something very amazing, and also that tells you something which is hidden in this proof. There is something related to the complex structure or something. I'm not so sure that what really is there. But so this should be remarked. And the next topic I'd like to talk about is the rigidity. So you have, and in the last two talks, so I just mentioned the rigidity, infinitesimal rigidity of the Thurston metric, but I've never proved that in the talks. The same kind of infinitesimal rigidity holds for the earthquake metric. And the proof is somehow can be done independently. So you, for instance, you can prove that just by using this and rigidity for the Thurston metric. But what I'd like to explain today is the proof independent of this duality. And actually the proof is shorter than the case of the Thurston metric in the earthquake case. So let me state the theorem. So let F, so this is the infinitesimal version. So we consider a norm to another tangent space with the same norm, the earthquake norm, be a linear isometry. Then there is a G, which is the diffeomorphism from S to S, such that Y is the image of this. So this induces a self-homeomorphism on the Teichmüller space that takes X to Y, and its derivative is equal to the F given here. Okay. So this should be called the infinitesimal rigidity. So by the way, for the original metric of the Teichmüller space, which is the Teichmüller metric, there was such a kind of the rigidity, a bit different of the statement because of the circle action in the case of the Teichmüller metric. But anyway, so it's called a Roydens rigidity. So Roydens showed that such a kind of thing. So if you consider the space of the holomorphic quadratic differential to holomorphic quadratic differential, which is a linear isometry, then what you get is just the action of the mapping class group combined with the scalar action, the complex scalar action. So there is a S1 ambiguity in that case, but this is quite similar to this kind of theorem. So is there any question about the statement? Is this clear? So we can prove this theorem by the following, combining following two arguments. So the first is as following. So and this is a kind of observation probably. So suppose lambda mu is in the measured lamination space. I haven't defined this, but so this is this was already defined, but I'd like to use this symbol E lambda hat to define by dividing this by length. So that should lie in a unit sphere. Okay. So just you normalize it so that its norm is equal to 1. So here's the observation. So if you consider two images of the two normalized earthquake vectors, and you consider the norm of that, then it's equal to the sum of this norm if and only if lambda and mu doesn't intersect transversely.
So the intersection
Intersection number, oh, sorry. It's 0, okay. Okay. So let me prove that. So this direction is easier. So if this is 0, then if they don't intersect transversely, then the union or probably plus of them. So if they share some component, then we just add up their measures, and you can consider that this is the sum of these two. And then length, you can consider the earthquake with respect to that. And the earthquake with respect to that is equal to just the earthquake, this one plus earthquake, this one. So that this whole in this situation. And also we have the length of this sum is equal to the length of this sum. Well, probably to prove that because it's normalized, we just assume that the length of lambda equal length of y is equal to 1, it's okay to just, we are considering like that, so that we just normalize from the start, and then you can consider that case when, oh, sorry, mu. Okay. Anyway, so that we have such kind of equality, and then this is also equality. So this is the norm of this sum. And as this one holds, this is just the norm of the sum. Whereas if you consider that something like that, just the plus of the length, then it's just by definition it's something like this. So these two must be equal. So that's simple. So the other direction is much harder to show. But what we have to show is a contraposition of this one, so that you consider the case when this is not equal to 0. Okay? And we consider the sum, well, which was the same as, because we normalize this is the same as, anyway. So then because this is another vector, another tangent vector, by Kirchhoff's theorem, there exists nu which realizes this as an earthquake. And now extend this nu to a maximal geodesic lamination so that we can define a stretch map such that so there are infinitely many ways to extend nu to a maximum geodesic lamination if the lambda itself is not maxima. But we can, because of that, if it's maximal, then at least one of them must intersect this transversely, because they have a non-trivial intersection number. Okay. So suppose this is the case. Well, if this is the case, then you can just change the names of them. Okay. So now, so the norm of this one was 1 because of the normalization. The norm of this one was just oh, sorry. The norm of this one is 1, and the norm of this one is also 1. So what we have to show is the norm of this one is less than 2. Then the proof is done. Okay, like to show. Okay. Now, we have, because of that, if you consider stretch vector along nu tilde of the, and if you just measure the length, this should be the less than, because they intersect transversely. The lambda cannot be stretched by nu tilde by the maximal length. So that means the length of lambda. So that should be less than 1 because of that. Assume that. And in general, this should be the maximal possible value is the length of the mu. The length of the mu at x, and which is assumed to be 1. So this is less than or equal to 1. Okay. So because of that, then taking the dual, then the dl nu is equal to d L lambda plus dl mu. So considering just putting them there, this should be equal to the B nu, or probably it's better to write it as d of the dl nu V nu is equal to the dl lambda plus dl mu V nu equal to the V nu of L lambda plus V nu of L mu. So, and the sum of them, so which is less than 2. Okay. So, because the length of that is less than, so that means that this is, sorry. So this is equal to the length of the nu at the x, which is equal to the R squared norm of E sub mu. So this is less than 2. So that's what we wanted. Any questions? Okay, so now, so we have how to put this? So we have f from the tangent space. So we have f from the tangent space to the tangent space. So that's our situation. So, and we can embed the projective lamination space to the unit sphere of the tangent space by taking lambda to E sub lambda. So this is what we write it by Ex. And we have just the inverse of this map, and which should be EY inverse. So composing them, we get the map from the projective lamination space to projective major lamination space, sorry. Projective major lamination space to projective major lamination space. And there's one property we have that it preserves this, the nullity of the intersection number. So if the two major lamination have 0 intersection number, then its image has the same property. That's the property of that. So we have a homeomorphism from projective lamination space to projective lamination space with this property. And actually there is a work of myself and Athanase saying that such a map always comes from mapping class. Induced from mapping class group action. So we have some G from S to S such that probably F is induced. This is what's a good thing? This induces this map. Okay. So that means so for any lamination, any projective lamination, if you consider this map, then it's equal to just the image of lambda under this G, or probably it's better to like this. So it's just map lambda by this G, and I consider the image, which is also the major lamination, then they should be equal. So, how long? It's just 10 minutes, okay. So this is actually the first step of the proof, and this shows that this part, but we haven't yet showed this part. I mean, actually this part should be written after that, but anyway, so that what's shown there is just the induced map is equal to F. But we still don't know that G takes the point X to Y. So there's another argument to show that. So dg x is equal to Y. To show that we well, let me first remark that if you consider this one divided by the length, so it's E sub lambda. Then norm of this one is equal to 1, right? So this is 1 by definition. So if you take this vector by lambda, by F, then, well, by this fact, it is mapped to a G lambda in a Y. So it's so this is again this is the norm of this one equal to the norm of this one. This is again 1. Okay. All right. So the length of Y of the G, suppose that this is equal to that, but we don't know how they are related. So that what the norm of this one and the norm of this one. So the norm of this one is equal to the length x and lambda, and the norm of this one is equal to the length of the G lambda. So this might be different, but there is some scalar that between them to relate them. So what we have to show is that this constant doesn't depend on the choice of the lambda. Okay. This k, so apparently this k depends on lambda. For each different lambda, you have a different constant. So if this k doesn't depend on lambda, we can see that, we can see that actually y should be dg star by the rigidity of the projective length spectrum. So that means that if you consider that the length spectrum so for each hyperbolic metric, we can consider the length spectrum with respect to the simple closed curves. And so it's the image lies in the space of the non-negative or positive functions defined on the space of the simple closed curve C. So, and even after projectivization, it's known to be the injective. So if we can show that in a project class they are equal, then we can show that y is equal to the image of that. And what we do is this constant k is the same when. This should be. So here we don't have the independence of the k with respect to the measured lamination. So this should be written as the k sub lambda. So what we show is that if the intersection number is 0, then the constants must be the same. And so then after that, so then what we can do is something like that. In the curve complex, so your curve complex was what? So it's a set of the simple closed curves, and if they are disjoint, they were joined by an edge in the curve complex. And it's known that the curve complex is connected. That means for any two simple closed curves, there's a sequence of the simple closed curves, and each adjacent ones are disjoint. So then for the disjoint one, these constants are the same. So by transitivity, so that for any two simple closed curves, this must be the same. Okay, by this kind of argument, we can show that this k lambda is actually doesn't depend on lambda. So that's a proof. So by this kind of argument, we can show that this kind of rigidity. So in the remaining 2 minutes, let me just mention that there are other kinds of properties we have proved. So one is this. So this is not complete. So this is asymmetric metric, but there is a notion of the completeness for the asymmetric metric. So we consider the forward Cauchy sequence, and if a forward Cauchy sequence converges, then it's called forward complete. So this is not, space is not forward complete. And actually, it's very similar to the Bayes-Peterson. This is quasi-isometric to the Bayes-Peterson. So that in particular, if you try to pinch this one to this kind of the stable curve, then we can do that in a finite distance. So, and we can consider something called like a forward completion of this space. And what you get is the same as the completion with respect to the Bayes-Peterson metric. That augmented Teichmüller space appears as the forward completion of this metric. Sorry, the time is up. So thank you very much for listening.
Any questions?
Yep.
So you had the estimate on the length of the earthquake path, which is like ml squared for the simple geodesic.
Yeah.
Is that true in more generality? Like if you take the earthquake path with some
earthquake, for the earthquake path, you have the same kind of length. So if you consider earthquake path, then its length is something like that.
So it's just t times the length of lambda squared in the base point?
Oh yeah, so if you go distance, there's something like a t, then you can have a t times length or something like that. So that because it just comes from the definition.
Okay. So that's like an upper bound on the distance between the
Yes, that gives upper bound.
Are there any sort of lower bounds?
Oh, that's very bad upper bound because as I said, this is this is the length of the earthquake path, and this kind of thing is much shorter. So we don't have an exact lower bound, but for instance, for some curve like something like a pinching, again we have the upper bound. So that we don't have actually good lower bound for general setting.
So in the sense that so there was the comment about earthquake paths being horocycle flow lines with respect to the Teichmüller metric.
Yeah.
So in the earthquake metric, is it expected that it happens that if you start from a point and then flow along the earthquake path for a long time, then it will sort of come back to itself?
Sorry that I get it. So that if
So if you take x,
Yeah.
then some lambda, measured lamination, and you take E sub T lambda.
Oh, it goes forever. It's just so you are in a Teichmüller space, so you can never come back to the starting point. It's go to the end. Always.
Not to the same point, but close to the same point.
No, never.
Okay.
So what's interesting is just the global behavior of the geodesic. So in the case of the wave Peterson, for instance, if you just go close to the pinching surface, augmented type, so a boundary, and then if you stay there, like then it might give a geodesic. So it seems the same kind of thing might happen for this earthquake metric. So if you go to near to this pinched point, then if you just travel there, then it might give a geodesic. But we haven't proven it. So we need something more to just prove that general behavior, to describe the general behavior of the geodesics.
So there's also a grafting operation.
Oh yeah.
Is that a metric
Yes. I think we have a complex version of this actually. That's another kind of the research which should pursue. You have a bending. So it's just a complex version of the earthquake. And this kind of metric should be defined on a bending also as an imaginary direction. And that can give some kind of the metric for the quasi-Fuchsian group. So that might be, again, an interesting topic, and we would like to continue to study.
Any other questions? Yes, I have one question here.
Yep.
So suppose you, Mike.
You own the mic.
Yeah. So suppose you do this most efficient pinching.
Yep.
Is that
There should be the most efficient, because there should be always geodesic. There should be some efficient pinching like that. But what we have is just upper bound. So it's obtained as a concatenation of the earthquake path, actually. The small amount of the earthquake with it. So each time we change the earthquake and to change it, and taking a sum, infinite sum, and you get the finite number. That's what we have. So
it decreases geometrically, like in the Will-Peterson case. It's like summing a geometric series mostly. Is that roughly what it is?
yeah.
That was one of my questions. Can you say a few words about why K lambda is the same as K mu?
Oh, so if they are, okay, if they are disjoint, so the point is here.
Yeah, right.
So it's, well, let me just check. So it's actually something like that. So let me, so it's because the length is so if you have so length lambda length g, so here the xy, so the times ey g lambda or something like that. So you have this one for mu and lambda plus mu. And because they are disjoint, the sum of this one and that one should be equal to that. Because the length, because this is the image of the ex lambda by f. What I forgot the symbol. So the sum of this should be the sum for the same expression for that. So that means so by the linear independence of these vectors, so what you get is that this is equal to the plus g lambda plus and mu. So by this intermediate term, you see that this is equal to this. So that's the point.
Any other questions? Okay, let's thank.
Good.